right before we left for lunch. So we're talking about every simulation is going to give us a different result. So that's why that does that. So here's what happened. They took 30 kids in a class and they all did the simulation. Okay. And then once they had done the simulation, they plotted the dots. Okay. So if 30 students did it, how many dots are on the graph? 30. Okay. So there's 30 dots on the graph and they represent every student, okay, who was doing the simulation. So let's talk about what does the dot above 70% represent? Okay, what does that dot represent? One student's simulation data. Okay, so one student's simulation resulted in a 70% free throw percentage. Okay, so that's what that one dot represents. So that's one of the things it's going to ask you today. What does this one dot on the dot plot represent? Chase. Okay, so that's one student simulation. All right, now this is where we estimate probability when we've got a chart like this, a dot plot, and it's really no different than what we did in the past when we looked at dot plots. It says use the results to estimate the probability that Miss Gallus would make 70% or less, okay, when shooting her free throws. So let's look. How many dots are 70% or less? Two. Okay. Out of how many total dots? 30. Okay. And so to make that a percent, we're going to divide, right? And so 2 out of 30 gives me 0.067, okay? We're going to leave our probability as a decimal, so you're not going to need to multiply by 100, okay? So this is my probability, okay? So we're just counting how many meet the criteria out of the total, right? So today is really just about understanding what the dots represent, knowing how to do like a get that probability, a percent, and things like that. Okay, so let's just look at a couple of examples. We're not going to do a bunch, and I'm going to let y'all loose. Okay. All right, so flip it over to the back. All right, so randomness, probability, and simulation. So our first learning target was about probability. Okay. It's just the relative frequency after many simulations. Or many, let's call it trials. Okay. After many trials. The longer we do it, the more accurate. Okay, so that's probability. It's just a relative frequency. It's a percent. All right, it's a decimal after many trials. Okay, how many did we get out of how many times we did it? Just like Miss Gallus and her free throws. Okay. The second thing is the law of large numbers. Okay, and the law of large numbers basically says if we do something many, many times, and it says many, many every time, many, many. Okay, the number of desired outcomes approaches its probability. So the law of large numbers, if we do something many, many times, the number of desired outcomes approaches its probability. That's what happened in my simulation. When I shot one shot, Miss Gallus had 100% free throw rate. When I got to 50, she was more at 80, which was more accurate. Okay, so the more I do it, the closer I'm gonna get to the actual probability. Okay. And then a simulation is just anything that we do to model chance. So just anything that we do to model chance. That's the simulation. Okay, we're not going to do the examples on the back of that page. We're going to do the ones that I did, the shorter ones. Okay, and we're only going to do 3 of the 4. All right, so let's jump over and let's look at this one. Okay, who eats breakfast? According to the Book of Odds, the probability that a randomly selected U.S. adult usually eats breakfast is 0.61. Okay, what does that probability mean?
61% of adults.
Yep. 61% of adults eat breakfast. That's what it says. Okay, that's 61% of adults eat breakfast. We want to clarify that if we take a large random sample. Okay, if I only took 5 people, probably wouldn't hit 61%. Okay, but if I take a large random sample, 61% of the adults eat breakfast. That's what it means. Okay. And then for question B, if a researcher randomly selects 100 people, will exactly 61 of them eat breakfast? No. Okay? No 2 simulations are the same. Good. This to me kind of feels common sensey. Okay, just kind of explaining what it means. Alrighty. All right, let's look at the next one. Oh, she did. Okay. Right. So let's look at this one. A husband and wife decide to have children until they have at least 1 child of each sex. Okay. The couple had 7 girls in a row. The doctor assured them that they were much more likely to have a boy for their next child after all those girls. Why is he wrong? It's probably going to be another girl, right? He's manipulating the law of large numbers, okay? He's manipulating that law. Because what's your chance of getting a boy or a girl every time? It doesn't change. It is a 50-50 chance every time, okay? So the fact that he's had 7 girls in a row does not guarantee there would be a boy next time, all right? So it's just a manipulation of the law of large numbers. Okay. It's just a manipulation. We can't use it that way. We've got to do one thing over and over and over again. And with talking about the sex of a child, you could have lots of different, or you could have 2 different options there. Okay. All right. And then we're going to skip the next one. All right. And then let's go to the one on the back. So this is one where there's that chart. So I wanted you to see one with the dot plot. Let's walk through that. Okay. So 50 repetitions of a simulation were carried out. The dot plot shows the number of cereal boxes that it took to get all 5 drivers' cards in each repetition. So I'm assuming that there's like prizes in the cereal box you're trying to get. Did anybody get all of the Nugget Croc things from the Happy Meal toys? We used to do that as little kids. When they'd have our favorite toy, we'd go and try to get all the different ones. Anyway, the Smurf glasses were my favorite. Do y'all know what the Smurfs are? It was a cartoon. It was the cartoon way back in the day. But
like they have made so many movies.
okay, no. I'm talking about the real Smurf cartoon.
Yeah, the one on the VCR.
The one on, she said on the VCR. I am 100. Yeah, I watched those live when they first came out on Saturday morning. I'm just saying I'm old. Y'all are young. On Boomerang. Oh, that's where the rerun shows are. Okay, all right. I did not watch the Flintstones in their original debut, but I did watch Woody Woodpecker in his original debut. Okay. Yeah. Every day when I got home from school, Woody Woodpecker came on. Yeah, I love Woody Woodpecker.
I got the movies that I got from the red box and I took them back.
Stop it. Okay, so let's look at this one, okay? So it asked me to explain what does the dot at 20 represent? Okay, so in this situation, what does that one dot represent? Well, it is that in one simulation, it took 20 boxes to get the cards. Okay. So that's what that one dot represents. There'll be some drop-down menus where you have to talk about that. Okay. Then on the next one, it says, use the results of the simulation to estimate the probability that it will take 23 or more boxes to get a full set of cards. So we're just going to look at this data. Okay. How many dots are 23 or more? 2 out of how many dots did they tell me were on there? 50. Okay. So 2 out of 50, we'd use our calculator and just divide. I don't know. 0.04. Okay. All right. So 0.04 would be our probability. Okay. Now, look at D. It says, based on the actual result of 23 boxes in your answer to part C, is there convincing evidence that the 5 drivers' cards are not equally likely? That's kind of a weird question. All right. So do we have convincing evidence, okay, that you got a better chance to get one card over the other? They put more of one card in the boxes versus another. Okay, it's kind of what we're looking at. Because it's a 4% chance it's going to take you 23 boxes to do it. Okay? I would say that we've got convincing evidence that it's not equally likely, right? Because some of these, it only took 5 boxes. But where are most of them? Over. They're 10 plus, right? It's going to take 10 plus. So I think that would say that's convincing evidence that we are going to have to do more than just 5 boxes of cereal. Okay? So that's that. All right. There you go. I can't remember. I think there's 6. Thank you. 6 questions. I was like, it's 5 or 6. I couldn't remember. All right. If you need a sequel, let's go do that right now. Okay?